Good morning. Today we are going to discuss problems on when the body is subjected to stresses in both the directions and problems on the elastic constants and change of the dimensions. In the last class we have discussed regarding the in the last class we have discussed regarding the uh, uh, stresses produced due to tightening of the nuts and also lateral strain, longitudinal strain, volumetric strain, and volumetric strain in a axial when axial load is applied along the circular bar and and also volumetric strain when triaxial loads are acting. And we also discussed the problems regarding this forces and all. In today's class, we are going to discuss few problems related to the change of the dimensions and the elastic constants, and also uh, when the body is subjected to stresses in both x and y directions. So let us do the problems. So first, so MS bar has a diameter of 10 mm and is 350 mm long. Tensile load of 15 kilonewtons is applied longitudinally. Calculate the extension of the bar, the change in diameter and change in volume. Assume modulus of elasticity of steel is equal to 2 into 10 to the power of 5 Newton per mm square and Poisson's ratio is 0.25. So what all given here? So here given that a mild steel bar, MS is nothing but a mild steel bar which is of a diameter 10 mm and is long 350 mm. Uh, and this is applied longitudinally by a load of 15 kilonewtons. Now we have to calculate the extension in the bar, that is nothing but delta L, and change in the diameter, that is delta D, and also change in the volume, that is delta V, and given ES equal to 2 into 10 to the power of 5. So in yesterday's class we have discussed longitudinal strain. It is nothing but change in length by original length. E is equal. Next we have discussed lateral strain. So lateral strain is nothing but the strain produced in the perpendicular plane to the applied force. So the strain produced in the direction of the applied force is longitudinal strain. The strain produced in a plane perpendicular to that of applied force is lateral strain. So lateral strain can be delta D by D for a circular cross-sectional bars. If you take a rectangular bar, then delta T by T or delta B by B will be the lateral strain, and longitudinal strain will be delta L by L. So longitudinal strain is generally acting along the length for the axial loads. Now, so given diameter of the bar is D is equal to 10 mm. Now area of that cross section is pi d square by 4. So instead of D we are substituting 10 mm. So we'll get pi into 10 square by 4. So that is equal to 25 pi mm square. And given length of the bar is 350 mm and tensile load is equal to 15 kilonewtons. So tensile load means its length is increasing and its diameter is decreasing, right? So load is 15 into 10 to the power of 3 newtons. Next, stress in the bar is sigma is equal to load by area. So stress induced stress is nothing but force by area, that is 15 into 10 to the power of 3 by 25 pi. So you will get a value of 190.98 Newton per mm square. Next, increase in length. So increase in length is nothing but, so stress along the length. So delta L is equal to stress into original length by modulus of elasticity. So it is sigma into L by E. So this one we derived from the formula of modulus of elasticity. So increase in length delta L is equal to sigma into L by ES. So 190.098 is the stress and 350 is the length by modulus of elasticity is 2 into 10 to the power of 5. Now the longitudinal strain E is equal to, so as you know, longitudinal strain is nothing but the strain produced along the direction of the force applied, right? So the strain produced along the direction of the force applied. Now that is 9 point, it is delta L by L. So that is equal to 0.334 by 350. Okay, so now that can be written as 9.549 into 10 to the power of minus 4. Next, lateral strain, it is delta D by T. So that can be written as 1 by M into delta L by L. So the delta D is equal to 1 by M into E. So into D. So 1 by M is nothing but Poisson's ratio. It is 0.25. E is longitudinal strain, that is 9.549 into 10 to the power of minus 4 into uh, D value is 10. Diameter is 10. So you will get the change in diameter is 2.387 into 10 to the power of minus 3 m. Means that much of diameter is going to be decreased. Next, so a change in the volume. We know that dV by V is equal to sigma by Es into 1 minus 2 by m. So this is the volumetric strain when subjected to an axial load. When subjected to an axial load, and dV is equal to V into sigma by Es into 1 minus 2 by m. So V is simply pi d square into L. So pi d square, instead of pi d square into L, we are substituting pi into d square is 10 square into L is 350 by 4 into, so V formula is pi d square by 4 into L, and sigma is 190.98 by 2 into 10 to the power of 5 into 1 minus 2 by m. 1 by 0.5, 1 by 8 can be written as 0.25. So it is simply the change in the volume is 13.11 meter square, meter cube. So this is the change in the volume. Next, okay. Next, so in a tensile test, in a tensile test on a steel tube of external diameter 18 mm, the external diameter 18 mm, 12 bore, an axial load of 1.7 kilonewton, produced an elongation of 0.0045 mm in a length of 75 mm, while the outer diameter suffered a compression of calculate values of Poisson's ratio, Young's modulus, shear modulus and bulk modulus. Area of cross section is equal to, so given that the steel tube's external diameter is 18 mm and 12 mm internal diameter, and it is subjected to an elongation of 0.0045 and the load is 1.7 kilonewtons and the length is 75 mm. Now the outer diameter is suffered by a compression of 0.00032 mm. Now we need to calculate the Poisson's ratio. Mu, that is nothing but lateral strain by longitudinal strain. Next, Young's modulus, it is stress by strain, and shear modulus and bulk modulus. So we are going to make use of the relations between all the elastic constants for this particular problem. So given that area of the cross section is uh, pi by 4 into d square minus d square, since it is a hollow steel tube. So capital D is 18 mm and small d is 12 mm. So stress induced is nothing but sigma is equal to load by area. The load, axial load is 1.7 kilonewtons. Simply 1.7 into 10 to the power of 3 by area is 141.37 mm square. Now linear strain is nothing but the longitudinal strain is nothing but the strain which is produced along the uh, along the uh, direction of the force. It is how much sigma is equal to E is equal to delta L by L. It is simply, so elongation of the length is given, that is 0.0045 by the length, actual length is 75 mm. And when, as you know, when you are applying the tensile load, the length increases and the uh, uh, di diameter decreases. So now the decrease in the diameter is it is 0.0032 by 18. So it is simply 1.78 into 10 to the power of minus 3. Now Poisson's ratio, it is nothing but the ratio of lateral strain to that of longitudinal strain. So it is 1.78 into 10 to the power of minus 5 by 6 into 10 to the power of minus 5. So you will get a value of 0.2967. Next, Young's modulus. So it is simply Young's modulus is equal to Young's modulus is simply, it is equal to stress by strain. It is 12.025 by 6 into 10 to the power of minus 5. So you will get a value of 2.004 into 10 to the power of 5 Newton per mm square. Next, shear modulus. So modulus of rigidity. So we know that the relation between the modulus of rigidity and modulus of elasticity is E is equal to 2C into 1 plus 1 by m. So just we'll substitute instead of E 2.004 into 10 to the power of 5, and C, instead of C we are substituting we are going to find C, and instead of 1 by m we are substituting 0.2967. So shear modulus C is equal to 2.004 into 10 to the power of 5 by 2.5934. Okay. So now this is how we'll make it. Now next uh, we have to calculate the bulk modulus. So for bulk modulus, we know the formula E is equal to 3K into 1 minus 2 by m. This is the relation between modulus of elasticity and the bulk modulus. So E is equal to 3K into 1 minus 2 by m. E we already know, that is 2.004 into 10 to the power of 5, and K value is already we know. Sorry, K value is what to be found. So it is K is equal to 2.004 into 10 to the power of 5 by 1.2198. So you will get a value of 1.64 into 10 to the power of 5 Newton per mm square. So this is how we are going to calculate the bulk modulus and the shear modulus and Young's modulus and the Poisson's ratio. Next, let us consider a problem which is a bar of a bar of 16 mm dia is subjected to a pull of 27 kilonewtons. The measured extension over gauge length of 80 mm is 0.12 mm and the change in diameter is 0.007 mm. Find the Poisson's ratio and the modulus of elasticity. Now, diameter of the bar is 16 mm. Area of the cross section will be pi d square by 4. It is simply pi into 16 square by 4. So you will get a value of 64 pi mm square. Next, given that pull is 27 kilonewtons, it is nothing but the tensile load P is equal to 27 kilonewtons. So you can write it as 27 into 10 to the power of 3 newtons. Next, so the gauge length is 8, L is 80 mm and delta L is 0.12 mm. Next, delta D is 0.07 mm. Now we need to find Poisson's ratio 1 by m and the modulus of elasticity. So the longitudinal strain is simply change in length by original length. So it is 0.12 by 80. So you can get a value of 1.5 into 10 to the power of minus 3. Next, lateral strain is delta D by T. So we will get 0.007 by 16. So it is equal to 4.378 into 10 to the power of minus 4. Now the Poisson's ratio is 1 by m, which is nothing but mu, that is equal to lateral strain by longitudinal strain. So the lateral strain what we got is 4.378 into 10 to the power of minus 4 by 1.5 into 10 to the power of minus 3. So you will get 0.29 as the Poisson's ratio. And moreover, the modulus of elasticity is simply stress by strain. The stress we obtained is 134.28 and the strain is 1.5 into 10 to the power of minus 3. So you will get an answer of 0.89 into 10 to the power of 5 Newton per mm square. Next, a cylindrical bar is 20 mm in diameter and is 20 mm in diameter and 1 meter long. During a tensile test, it was found that the longitudinal strain is 4 times the lateral strain. Calculate the modulus of elasticity and bulk modulus. If its elastic modulus is 1 into 10 to the power of 5 Newton per mm square, find the change in volume when the bar is subjected to hydrostatic pressure of 100 Newton per mm square. So it is given that a cylindrical bar. So cylindrical bar means it will have a length and a diameter. So the diameter is 20 mm and the length is 1 meter. It is nothing but 1000 mm. Now during this tensile test, the longitudinal strain is 4 times of lateral strain. Means lateral strain by longitudinal strain is equal to 1 by 4. That is nothing but 0.25. It means our Poisson's ratio is 0.25. We need to calculate modulus of rigidity and bulk modulus, and given that modulus of elasticity is 1 into 10 to the power of 5 Newton per mm square and the pressure is 100 Newton per mm square. So we know modulus of elasticity 1 into 10 to the power of 5 and from the condition longitudinal strain is 4 times the lateral strain. So we know that uh, Poisson's ratio is 0.25. So now first modulus of elasticity, rigidity. So we know the relation between the modulus of rigidity and modulus of elasticity. It is simply E is equal to 2C into 1 plus 1 by M. So 1 into 10 to the power of 5 is equal to 2C into 1 plus 0.25. So C value is simply 1 into 10 to the power of 5 by 2 into 1.25. So you will get C value as 0.4 into 10 to the power of 5 Newton per mm square. Next, bulk modulus. It is simply E is equal to 3K into 1 minus 2 by M. So E value is 1 into 10 to the power of 5 and 3K is what you need to find and 1 minus 2 into 0.25. So K is equal to 1 into 10 to the power of 5 by 3 into 0.5. So this is equal to 0.67 into 10 to the power of 5 Newton per mm square. So this is all what we get. Next, so change in the volume. It is simply, we know that modulus of bulk modulus is equal to direct stress by volumetric strain. So volumetric strain is equal to bulk modulus by direct stress by volumetric strain, bulk modulus. So EV is equal to direct stress sigma by K. Okay. Now 100 by 0.67 into 10 to the power of 6. So here that dV is equal to, we know that delta V by V is equal to EV. So delta V equal to EV into V. So V, you know, volume of a cylinder is pi d square into L by 4. So that will give you a value of 469 mm cube. Okay. So this is how you calculate. So we are making use of the bulk modulus formula, that is direct stress by volumetric strain. We are given with direct stress and bulk modulus, so we can find volumetric strain from that. But we know that EV, volumetric strain, is simply change in volume by original volume, that is dV by V. We know that formula for V is pi d square L by 4. So the overallly you can get the change in volume, that is 469 mm cube. Next, so this is a repeatedly asked question. A steel plate 120 mm long and 40 mm wide is subjected to a tensile stress of 50 Newton per mm square and a compressive stress of 80 Newton per mm square as shown in the figure. If E is equal to 2.07 into 10 to the power of 5 Newton per mm square and Poisson's ratio is 0.3, calculate the change in length and width of the plate. So given that there are two stresses, one is along the x-axis, it is a tensile stress, sigma x is a tensile stress and its value is 50 newtons. So this will lead to the increase in the length and at the same time it will lead to the compression along the y-axis. So it is extending in the x-axis means it will compress in the y-axis. Next, one more stress is there, that is 50 Newton per mm square. So this is compressing the width. So in the y-axis if it is compressing means, so it will extend in the, its effect is compression in the y-axis. So if it is compressing the y-axis, then it will extend in the x-axis. So the decrease in the diameter due to the compressive force will also lead to the extension, its elongation in its length. So here you can have two strains. So strain in the x-axis is simply sigma x by E minus sigma y by ME. Next, strain in the y-axis will be sigma y by E minus sigma x by ME. So now first, stress given in the x-axis is 50 Newton per mm square. Now stress in the y-axis is minus 80 Newton per mm square because it is a compressive one and it is acting in the negative direction. So now strain in the x-axis is, so Ex equal to sigma x by E minus sigma y by Me. So this is due to the effect of the compressive force. So 50 by 2.07 into 10 to the power of 5 plus 80 into 0.3 by 2.07 into 10 to the power of 5. So you will get the stress in the x direction 0.357 into 10 to the power of minus 3. Next, so stress, but we know that stress in the x direction is simply change in length by original length. So the change in length will be 0.357 into 10 to the power of minus 3 and given its length as 120. So you'll simply substitute instead of L 120. So you'll get change in length as 0.0428 mm. Next, strain in the y-axis. So it is sigma y is equal to e to e suffix y is equal to minus sigma y by E minus sigma x by Me because the effect of both is a compressive force. So that is equal to minus 80 by 2.07 into the power of 5 minus 0.3 into 5 50 by 2.07 into 10 to the power of 5. So this will give you a value of 0.458 into 10 to the power of minus 3. So but we know that EY is nothing but change in breadth or change in thickness by thickness, but we are given with only the width. So we are writing in terms of width, that is delta B by B. So delta B will be 0.458 0.458 . Next, so one more problem. So previously we have taken two forces, so sigma x and sigma y. Now we are taking along the three forces, that is triaxial forces. So a metal flat plate 100 mm into 50 mm in cross section is 250 mm long. It carries a load of 400 kilonewtons in the direction of the length. Next, it carries a compressive load of 4 meganewtons on its 100 mm. Next, uh, and a tensile load of 2 meganewtons on its 50 by 25 mm forces faces. If E is equal to 200 kilonewton per mm square and Poisson's ratio is 0.25, find the change in volume of the bar. Okay. So given that a metal flat plate that is of length, its length is 100 and the height is 50, and its base and width are given, that is 150, and its length is 200. Okay. Now it carries a tensile load of 400 kilonewtons in the direction of its length. So here see, we have denoted it with x. So the length is along the x-axis, that is 250. So along this axis only its load is there, that is 400 kilonewtons. Next, a compressive load of 4 meganewtons on its 400 by 250 face. So it is on the top face, 100 by 250. It is 4 meganewtons. Next, tensile load of 50 by of 2 meganewtons on its 50 by 250. So this is 50 and this is 250. It is nothing but its face. About its face, it is 2 meganewtons. Now E value is given and Poisson's ratio is given. You need to find change in the volume of the bar. So we already know that Poisson's ratio is 0.25. It is given in the problem. Next, length of the flat is 250 mm. Next, width is 100 mm. Next, thickness is 50 mm. Now volume is simply LBH or LBT. So it is 50 into 100 into 250. It is equal to 125 into 10 to the power of 4 mm cube. So you can see in this particular problem that, see, along its length it is 400 kilonewtons, and on the face of 250 by 100 it is 4 meganewtons, and in the face of 50 by 250 it is 2 meganewtons. Okay. Now, so stress in the x direction, it is sigma x is equal to P by A. So if you see here, see, in the x direction it is 400 kilonewtons and its cross sectional area is 50 by 100. Okay, so 400 into 10 to the power of 3 by 50 into 100. This area you have to consider. Next, so if it is Py is 2 meganewtons, means 2 into 10 to the power of 6, and the by area is 50 into 250, because you have to consider this cross sectional area. Next, Pz, stress along the z direction, is 4 meganewtons by area, that is nothing but 4 into 10 to the power of 6 by area is how much? So 250 into 100. So that is what we have written. So for the first one, along the length 250, it is the cross sectional area is 50 by 100. Along this 100, along the y direction it is 250 by 50, and along the z direction it is 250 by 100. So you have to consider the cross sectional area but not along the directional area. So it is 400 by 60, and it is 2 into 10 to the power of 6, and next it is 4 into 10 to the power of 6. So along the z direction it is a compression. Next, strain in x direction. So we have three forces, so we have to take all the three. So it is sigma x by E minus sigma y by E me plus sigma z by me. So 80 minus 0.25 into 160. So just substitute the sigma x, y and z. So 0.25 is 1 by m value plus 0.25 into 60. So Ex is equal to simply 80 by E. Next, Ey. So Ey is also formula again. Sigma y by E minus sigma x by me plus sigma z by me. Because of compression we are taking like that. It is 160 minus 0.25 into 80 plus 0.25 into 160 by E. So you will get a value of 180 by E. Next, strain in the z direction. It is Ez equal to sigma z by E minus sigma x by me plus sigma y by me. Now this is equal to minus 160 minus 0.25 into 80 minus 0.25 into 160 by E. So you will get minus 220 by E. So if you are getting minus 220 by E, then then dv by v is equal to ex plus ey plus ez. So dv by v is equal to, just we are substituting 80 by e plus 180 by e minus 220 by e, and we know that v here it is a denominator. I am sending it to the right hand side, it is numerator there. So we know that v is equal to lbh because this is a rectangular block. Okay, so dv equal to 250 into 100 into 50 into 80 plus 180 minus 220 by 2 into 10 to the power of 5. So in this manner you will find 250 mm cube. This is the change in volume. So in today's class we have discussed, so there is an alternate solution for it. Simply dv by v is equal to sigma x plus sigma y plus sigma z by e into 1 minus 2 by m. So these all we have found, that is 80 plus 160 minus 160 by 2 into 10 to the power of 5 into 1 minus 2 into 0.25. So you will get a value of 40 by 2 into 10 to the power of 5. So dv is equal to, so 250 into 100 into, so it is 100 into 50 into 40 by 2 into 10 to the power of 5. So this 250 into 100 into 50 is simply the volume. Okay, so you will get a value of 250 mm cube. So this is how then alternate solution. So instead of going for the lengthy process, you can also go for this. So this is a very long process. So that is a shortcut method. So here we found sigma x, sigma y and sigma z, and we found strain along each direction, and we substituted that sum of all the strains is equal to dv by v. So there we have taken direct formula, that is dv by v equal to sigma x plus sigma y plus sigma z by e into 1 minus 2 by m. So this is how we calculate the problems. So in today's class we have discussed problems on change in the dimensions and longitudinal strain and lateral strain and the relations between the modulus of elasticity and modulus of rigidity and bulk modulus. And also we have discussed something the problem regarding the volumetric strain for the triaxial forces, and we have discussed the uh, so we have discussed the problem, everything we have discussed, right? So we have discussed regarding the axial forces, we have discussed regarding the biaxial forces. So in the tomorrow's class, we'll be discussing the thermal stresses, that is temperature stresses, and we'll solve few problems on the temperature stresses in the composite bars as well, and also temperature stresses in the single bars, and temperature stresses in the varying bars, and temperature stresses in the compound bars, and stresses due to tightening nut and temperature rise. So tomorrow we are going to conclude this chapter by finishing this temperature stresses completely, right? So by tomorrow we are going to end the second chapter. Okay, fine. So thank you very much, and we'll be meeting tomorrow again. Value net framework, and there is diamond framework, and there are so many. Depending on your context, depending on your situation, depending on your requirements, you can choose the appropriate framework for the analysis of the internal. One of the ones that I was actually focusing on this is the Pasteur framework, which is used for carrying out the external environment